Hello, I am Abhinav Pandey, a first-year student at Penn State Brandywine, presenting a video that is part of my honors project for a matrices class. This video is about finding the singular value decomposition of a matrix and its applications. What is a singular value decomposition? Well, a singular value decomposition is the factorization of an m by n matrix into three separate matrices, U, sigma, and V transpose. U is an m by m matrix containing left singular vectors of A. Sigma is a diagonal m by n matrix containing singular values of A. And V transpose is an n by n matrix containing the transpose of the eigenvectors of A. The process of finding the singular value decomposition is not complicated, but it is tedious. The first step is to find the orthogonal diagonalization of A transpose A. This step consists of finding eigenvalues of A transpose A and then finding the corresponding orthonormal sets of eigenvectors. The first step is to set up the n by n matrix V, which contains the orthonormal eigenvectors found in the previous step. In this step, first arrange the eigenvalues of A transpose A in descending order, then fill in the columns of V with the corresponding unit eigenvectors. The third step is to set up the matrix sigma, which is the one containing all the non-zero singular values, hence the name singular value decomposition. To set up this matrix, first put all the non-zero singular values of A transpose A in a diagonal matrix D, with the top left being the highest singular value, and the entries along the diagonal are the rest of the singular values in descending order. Next, set up the m by n matrix sigma, such that the top left corner of sigma is the matrix D and all other entries are 0. The fourth step is to set up the matrix U with m vectors. Vectors in U are normalized vectors that result from A times V sub I, where V are the eigenvectors present in the matrix we found beforehand. After finding the vectors U1 to UM, U can be set up with its columns containing these vectors. After all three matrices U, sigma, and V have been found, the singular value decomposition can be set up as their product, the only difference being that the transpose of V has to be put into the equation. For an example, we can find the singular value decomposition of the 2 by 3 matrix A containing the values 4, 8, 11, 7, 14, negative 2. The first step to this would be finding the orthogonal diagonalization of A transpose A. The matrix A transpose A is equal to 80, 100, 40, 100, 170, 140, 40, 140, 200. To find the eigenvalues of A transpose A, we find the roots of the characteristic polynomial, which in this case turns out to be 0, 90, and 360. Now we need to solve for the eigenvectors corresponding to these eigenvalues using this equation, and solve for x. For this, we get the vector x can be all values in the span of 1/2, 1, and 1, and then finding the unit vector in the span, we get 1/3, 2/3, 2/3. Using a similar process, we can find v2 and v3 to be negative 2/3, negative 1/3, 2/3, and negative 2/3, negative 2/3, and 1/3 respectively. And we can set up the matrix V as follows. The next step is to set up the matrix sigma. First, we need to find the singular values of the matrix A transpose A by square rooting the eigenvalues, and we got 6 root 10, 3 root 10, and 0. The matrix D can then be set up with the non-zero singular values as its diagonal entries in decreasing order. From here, we can fill up the 3 by 2 sigma with D on the top left and the rest of the spots with zeros. Now we can set up the 2 by 2 matrix U with the vectors U1 and U2. U1 can be found using the formula 1 over sigma sub 1 times the product of A and V1. The result is 3 over root 10, 1 over root 10. U2 can be found the same way by using sigma 1 and V2, and gives the result 1 over root 2 and negative 3 over root 2. These two vectors make up the matrix U. Now that all of these matrices have been found, we can write out the complete singular value decomposition as a product of U, sigma, and V transpose. But why bother putting in all this effort? What is the point of singular value decomposition? Singular value decomposition is most commonly used for data compression, more specifically for compressing images. If an image size is too large, they can be compressed using this method to reduce the amount of space they are taking by simply tweaking the sigma matrix. The basis for all this is the fact that images are basically matrices containing the values for all the colors in the image, and if a matrix exists, its factorization can be found. Let's take an easy example. Consider this 5x5 image. The pixel values for this image are given in the matrix A. Finding the singular value decomposition of A, we can get the following matrices for U and V. However, these are not the ones that we can tweak. Here we see the matrix sigma, which contains the singular values from the factorization. As you can see, 3 of the 5 values are very small compared to the other 2, which means that they can be changed to a 0 without much impact on the resulting image. Changing the matrix in this way results in the computer having to store less information, and as you can see from these before and after images, there is not much difference between the two other than an infinitesimally small amount of gray existing on the image on the left that is not present on the image on the right. That was a small image. Let's take a look at a larger image to see how compressing using singular value decomposition affects it. In this image, 61 singular values are left in the sigma matrix. There is a significant amount of difference between the original and final image. When 32 singular values are left, however, you can see that there is an even greater difference between the original and final image, and the final image is of a lower quality. These two changes are very drastic. However, usually during compression, the images are almost indistinguishable before and after, resulting in an easier to store file that does not lose its appeal. The big takeaways from this are that any m by n matrix A can be factored into the form U sigma V transpose using singular value decomposition. The matrix sigma, which is the middle one, contains the non-zero singular values of the matrix A. Zeros take up less space in a computer than other data values, and that removing insignificant singular values can compress images while maintaining image quality to almost the same extent as the original. Thank you.